32, Unit 6-2, page 352, a lot of twos, linear and angular velocity. Now, the first thing we want to talk about is angular displacement. And when we're talking about angular displacement, we would really be talking about the amount of rotation between the rays of that angle in a circular motion. Remember that an angle is a figure formed by two rays with a common endpoint. The two rays are called the sides. This is called the initial side, correct? And if we went to here, this would be called the terminal side. And so the amount of rotation is really angular displacement. And ever since we've been talking about angles, we've called it theta. And we would be considering theta in radians here. Okay, we're going to be dealing with theta in radians. So when we say angular displacement, we're just saying how big is the angle. Okay, that's really all we're saying. So if you see the word angular displacement, just think theta. That's how far I went. Remember, radians is really more how far instead of how many degrees. You understand it? It's the same thing, but it's really thinking about how far around we went in some kind of unit of length rather than in some kind of unit of degrees. Although there's some equivalences there based on the unit circle. Okay, so let's just do a couple of problems off of our worksheet. We'll just look at number 11 as it relates to this. Number 11. Number 11 says that something made 3 revolutions. 3 revolutions. And we want to know what the angular displacement is. In this section, we're going to be dealing with things like Ferris wheels, or wheels on the bus go round and round, or merry-go-rounds, things that go around in circles, and look at the linear velocity of an object that's on that wheel, or an object that's on that Ferris wheel, or the actual velocity of the wheel itself as far as displacement angular wise. But what we need to do first of all is think about the angular displacement, or the value of the angle in these situations. If we had an object like a merry-go-round and you were actually hanging on to that merry-go-round, and we'll get that out of there maybe. If this was a merry-go-round and you were out here and that merry-go-round was going around and around and around, we would try to talk about how far you went, and we would also want to talk about how fast are you going. Well, first of all, in rotations, we know that one rotation is how much? How much is a rotation in terms of pi? It's 2 pi, right? A circle's 2 pi in radians. So one rotation is equal to 2 pi radians, correct? So if we go 3 revolutions, then we would multiply 3 times 2 pi, and we would get 6 pi radians. Any questions on that? If you wanted a decimal, then you would multiply 6 times pi, and you would get approximately 18.8 radians. 6 pi is the exact answer. 18.8 is a rounded answer. So we need to realize that angular displacement is just talking about the size of the angle. And the reason we're calling it that is because we may be going around 2 or 3 or 4 or 5 times. We may be talking about the wheels on a school bus and you went 30 miles. How many times did that thing turn around? Or if you've got a drive shaft in a car and that drive shaft is spinning so many times, and that makes this gear turn and that other gear turn and that other gear turn, and eventually the wheel turns, how does all that stuff work together? So you can see that trigonometry starts leading into mechanical engineering and a lot of things like that, which we couldn't put a car on the highway or a man on the moon without some trigonometry, obviously. Okay, so we got angular displacement. Let's look at number 12. Excuse me. Number 12 said 13.2 revolutions. And so again, we would take the number of revolutions and multiply by 2 pi, because one revolution is a full circle, which is 2 pi radians. The radians are understood when you stick the pi there. We just kind of know it's radians. And we're going to have 26.4 pi radians as an exact answer. If we multiply times pi, then we would get 82.9 radians, and that's a rounded value. Any questions on angular displacement? Revolutions times 2 pi. Okay? All right. And that's theta, yes. Yeah, because it says in the directions, round to the nearest tenth, so that means you're going to go ahead and do that. And on this part of the test, I'm going to let you be using a calculator. Yes. If you left it 26.4 pi, probably wouldn't count it wrong, but following the directions, it says to the nearest tenth. All right. Now, let's talk about velocity. Now, I'm just going to get totally away from the unit circle and talk about velocity. If you were in my Algebra 1 class, what did we call velocity? Change in y, change in x. I mean, this is the kind of thing we were talking about, right? And even in Algebra 1, we said blah per blah. Well, give me some examples of velocity. Miles per hour. Feet per second. I mean, those are things that would be velocity, right? And so what kind of things are we talking about? Distance divided by time. So we know that velocity is the slope of our lines that we were doing with y equal mx plus b. It was the blah per blah. It was miles per hour, feet per second. But in reality, velocity is distance divided by time. Now, if we're talking about angular velocity, and we're going to define it to be distance divided by time, what is it that we call the distance that an angle traveled? What do we call that? The distance that the angle went. Like, here's my first ray, and here's my second ray. What is the distance? Isn't that theta? My distance is theta. I'm talking about angular velocity. I want the distance the angle went. Remember, if we talk about radian measure for an angle, we're really talking about distance, not degrees. We're not talking about degree clicks. We're talking about how far it went, radian clicks. And so my theta is actually the distance that it traveled around that circle, considering the unit circle, okay? And then we have time. So angular velocity then is theta divided by time. The Greek symbol that is assigned to this is a weird-looking W, which is called omega. And so angular velocity is theta divided by time, which is equal to W or omega. So my formula then is W equal theta over T. So there's our formula for angular velocity. So W from now on will stand for angular velocity. And its formula then is theta, the angle displacement, how far that traveled in radian clicks, if you want to call it that, divided by the time it took it to travel that far. Okay? Now, why are we saying it like that? Well, here's the deal. What's going to happen is we could be on this merry-go-round, you see, and some guy might be right out here, and somebody else might be right here, and somebody else might be right here. as far as angular velocity, who's going faster? Nobody. As far as angular velocity, they're going the same speed. They got the same number of clicks proportional to 2 pi as anybody else got in proportion to 2 pi in the same amount of time, you see. So angular velocity, when we think about theta, we're thinking about the movement in relationship to 2 pi. It's the same percentage here as it is here as it is here over the same amount of time. So angular velocity in all three of those positions is the same. You move the same radian degree in the same amount of time because theta is the same here, here, and here. Those are congruent angles, you see. Okay? Now, but the distance traveled not in radian clicks, but in inches or feet is going to be bigger as you go out. So your angular velocity is going to stay the same, but your linear, we'll talk about that in a minute, velocity is going to get bigger and bigger and bigger and bigger and bigger. Okay? All right. So let's talk then about angular velocity. Let's look at number 13 and 14. It says on 13 and 14 on the worksheet, determine the angular velocity round to the nearest tenth. The formula then is omega is equal to theta over time. Omega equals theta over time. Now, it gave us revolutions in seconds. What do we have to do with those revolutions? Number 13, excuse me. Number 13, we had 1.8 revolutions in 9 seconds. So we've got to get theta, correct? And theta is equal to the number of revolutions times 2 pi. And that's going to convert it to radians for us, right? And so we're going to have theta is equal to 3.6 pi radians, which if we rounded that to the nearest tenth, which we're not going to do, we'll wait to the very end, would be something. But anyway, we're not going to round to the very end. So now we've got our theta. So now our omega, our angular velocity, is the angular displacement theta, 36 pi radians, divided by the amount of time, seconds. And so we get 3.6 pi divided by 9, and we get, 3.6 divided by 3.6 pi divided by 9, and you get rounded 1.3. Notice our unit. Radians per second. 1.3 radians per second. Now, a radian click is a percentage, basically, of 2 pi, right? It's a certain percentage of 2 pi. So it's like 1.3 of those little clicks every second, okay? Now, we're still talking about the angle displacement. We're really not talking about how far we traveled on the outside of that circle. We're talking about creating that angle. How fast did it take us to create that angle, okay? Any questions on that? Okay, let's look at number 14. I'll put my formula back in just a second. So we've got our formula again. Omega is equal to theta divided by time. Number 14, it said 17.2 revolutions in 12 seconds. Again, we want theta divided by time, so we must first find theta, which is our angular displacement, the distance traveled in radian clicks, if you will. which is 17.2 times 2 pi. We take the number of revolutions. Each revolution is 2 pi. And so we would get 34.4 pi, which is going to be radians. And we would leave it like that for now. So we're going to plug that into our omega formula, our angular velocity formula. Angular velocity is equal to angular displacement theta, 34.4 pi radians, over time, which was 12 seconds. And so we would have 34.4 pi divided by 12, which would give us 9 radians per second. Now, what that's telling us is not the speed at which this person on this merry-go-round is going around. That would be linear velocity. It's telling you the speed at which the angle is being created. You understand that? How fast are we creating this angle? Not how fast is this object traveling out there. Okay? How fast the object is traveling out there is linear velocity. How fast the angle is being created is angular velocity. All right, everybody understand angular velocity? All right. Now, if we take that same scenario, and I'm going to remove this and kind of redraw, hoping to make sure we have a clear understanding of what's being discussed here. So let's go back to that merry-go-round. And we're going to think about if we had someone who was standing right here versus someone who was standing right here versus someone who was standing right here. As far as the speed at which the angle is being created is the same, right? The speed at which the angle is being created is the same, but because the distance that this person is from the center versus the distance that this person is from the center versus the distance that this person is from the center will cause them to actually be going faster, not in terms of angle creation, but in terms of how far they actually travel in feet. Because the little green guy isn't going to go as far every time he goes around as the one on the outside, right? He's going to go around a whole lot. He's going to go further every time he goes around. Well, what would tell us the relationship? Let's say that the green was 1 foot, and the blue was 2 foot, and the black was 3 foot from the center. Could you tell me just from right now a relationship between how fast they're going to be going as far as the distance traveled? Would you think that the blue dot is going to be going twice as fast as the green dot, and the black dot's going to be going 3 times as fast? Because what's not changing? Angular velocity. What's the only other factor? Radius. So the radius length must be that relationship, that scale factor, you see. Okay, so the linear velocity, I'll start again, linear velocity, the velocity at which that object is traveling, which we will call v for linear velocity. Just wanted to double check what they called it. is going to be what we already had, right? It's going to be our angular velocity, which was theta divided by time. And then what factor is going to change how far it actually goes? The radius. So linear velocity is going to be angular velocity times radius length. You see, that makes sense? And so our formula would be, if we write it the way it is in the book, r times theta over t, or what is theta over t? Omega, radius times omega, okay? But we know that omega is theta divided by time. So if you take theta divided by time, you have angular velocity. When you multiply by radius, it tells you how far they actually went, okay? And so we'll either be using this formula, or we'll be using this formula to actually get our angular velocity width before we plug in our radius, okay? So let's see what they give us here on number 14, the second 14. This has two 14s on it. So this is the second 14 on this page we see. We have that omega. What's that stand for? Angular velocity. We have angular velocity is 27.4 radians per second. And we have that the radius is 4 feet long. They gave us radius and angular velocity, so we just stick them straight in. So linear velocity v is equal to angular velocity omega, 27.4 radians per second, times radius of 4 feet. And we're going to get velocity is equal to 4 times 27.8 is 109.6 radian feet per second. Radian feet per second, okay? I put feet per second. I should have put radian feet per second. It's kind of understood that it's radian feet per second, okay? That kind of radian kind of got attached in there. But anyway, we're going 109.6 feet per second. You could change it into miles per hour if you wanted to do a lot of dimensional analysis, right? So how fast would they really be going in miles per hour? We'll do that in just a moment, just to show you how to do that. Let's look at number 15. Didn't want to go away. Number 15, we have angular velocity, omega, is 75.3 radians per second with a radius of 17 inches. We'll convert this one. It'll be even more fun. And so we're going to have that our linear velocity is 75.3 times 17, which is 1,280.1 inches per second. Any questions on that? Now let's try to make a visual of this. I'll get out of the way in just a second. I know you're trying to still take some of those notes. I'm going to move that. I'm going to draw a picture of this scenario to give you a little idea, yes? We can put rad inches per second, but the radians is actually kind of understood. As we calculated the value of omega, 75.3, that would have been in terms of theta being radians. So we could say kind of radian inches per second, but if you actually wanted to know how far you went, it's not really like 1280.1 times the value of a radian. See, we're not really going to plug the value of a radian in. We're just going to say 1,280.1 feet per second. The radian idea was in the angular velocity. And it's in the back of our mind, but it's not a part of the calculation as far as how far we went in inches. Now, let's look at this idea. Let's say that we actually had a circular thing. This could be a tire or a drive shaft or something. And what we've got created here is that there's something that's 17 inches, okay? Maybe there's a rock in your tire. A 17-inch diameter tire is a pretty big diameter tire, though, but it's not too bad. 17-inch, that'd be a 34-inch wheel. Let's just say there was a rock in the tire, and it was actually that big. Maybe it's a truck tire or a tractor tire. And you've got 75.3 radians per second. Now, there's 2 pi radians in a circle, which is 6 something. That's like going around 12 times. You understand there's about 3.14. There's 2 pi, 2 times 3.14, 6.28 radians in a circle. Well, 75.3 divided by that means that thing went around about 12 times in a second. This thing's moving. You kind of get the idea. We're dealing with a gear or a pulley or something that's moving pretty fast. Every second it's going. Okay, that's what's going on. So that thing went a long ways in a second. 1,280.1 inches. Spinning pretty quick. Like. Okay. Well, we want to know if something was, that tire's spinning real fast and there's a nail in it, how far did that nail actually go if he's going on the highway, or that rock in the tire, or whatever. Well, let's figure that out in miles per hour, just so we understand some dimensional analysis. Okay, so here's what we got. We've got 1,280.1 inches per second. Now, we need to do a bunch of conversions. See how many. Now, what do we know? We want to end up with what on bottom? Hours. Now, do we know how many seconds is in an hour? We need to lose the name seconds and gain the name hours. 1 hour is 3,600 seconds, right? Now we want to go from the name inches to the name miles. We want miles per hour. So we need to lose the name inches and gain the name miles. I'm not going to need that other. We just kind of went straight from one to the other. We know that 1 mile is 5,000. So we don't know, because we know how many inches in a foot and a foot in a mile. So let's go that way. Well, we don't know how many inches in a mile. So we're going to say, well, I do know how many inches are in a foot, right? I know that 1 foot is 12 inches. And so that'll get rid of the name inches, but now I got to get rid of the name feet. I know how many feet are in a mile, right? 1 mile is 5,280 feet. So now I lost the name feet. So what's left here is miles per hour. Everybody understand how to use dimensional analysis to convert? So if you do 1,280.1 times 3,600, divide 12, divide 5,280, what do you get? 1,280 times 0.1, times 3,600, divide 12, divide 5,280. Somebody got it? 72.7 miles per hour. Somebody's speeding by just a little bit if they're rocking their tires doing that. Anyway, so the problems that we have here we could come up with a realistic story of how to use those. And when you do your homework, there's going to be some realistic stories. We just kind of started with an equation and made up a story instead of starting with a story and making up an equation. You're going to have to go the other way. But hopefully you got the point. Any questions on linear and angular velocity? All right. Appreciate it.